Hello students, it's lecture number 18. Okay. We are into chapter number 4, but actually we are also doing some part of chapter 5 as well. However, the chapter 4, the content that I am going to talk about is given in the chapter 4 only. Okay. So far we looked at the test function differently. So, ux we have seen this as a piecewise polynomial. Okay. So, one domain we are dividing into number of elements. Okay. So, number of elements n is basically equal to number of elements is basically is equivalent of number of piecewise polynomial and each element has a certain number of nodes. So, number of nodes in each element has has a meaning. So, it depends on the number of variables that define the polynomial. So, basically what we have seen is number of nodes 2, then this is a linear ux. If 3, we see that this is quadratic ux. Similarly, if it is 4 nodes per element, then this will be cubic ux, right. So, this what it signifies. Okay. Now, our original equation, the weak formulation is, as we know, this will be 0 to L dw over dx Ea du over dx, right, is equal to 0 to L Wbx Wx dx. This is for the problem we are talking about. Okay. So, the same problem we are talking about when you have something like this. So, you have B given like this one. Okay. And this is the 1D elasticity problem. Okay. So, now what we did, we actually now we are looking this as a combination of. So, we are looking at we have divided these into number of elements. So, we are now looking at the single element, and from there we are going to sum it up for all the elements. So, basically the whole domain has been the total L has been converted into L1 plus L2 till number of elements, right. So, where n is a number of elements. Yeah. And within one we can like we formulate, and what do we find? So, we formulate within for each element we say u e x, that is u test function within that element is basically as a function of, we wrote something like this, n e I x e multiplied by u e I, and I equal to 1 to number of nodes, right. So, where here in this case a small n is equal to number of nodes in the element. Okay. So, same the W also we write the same way, and W E x becomes summation I equal to 1 to n, and then we have n I e x e, and we say W e I, okay, where these are the constant at each node. So, let us say this is one element, this one, and this will have a number of nodes within the elements. Let us say it is quadratic, there will be 3 nodes, and in this case this will be n equal to 3, right. So, at each node there will be a displacement value. So, this will be u e1, this will be u e2, or this could be u e3, something like that, yeah. And similarly there will be corresponding value of w as well, weight as well, which will be w e1, 2 and 3. Okay. Okay. So, this is how we wrote. The other way also we can write is u e x is equal to, we can write like this, n, right. This will be n e1, n e2 and so on till n e n, this multiplied by, you have u e1, u e2 till u e n, right. So, you can also write this way, okay, or this is also known, you can write it as n matrix. This is the n matrix, right, multiplied by, you can say this is u e, you can say this is u e matrix, u e vector. So, this is something like this, where this is n matrix, or n basically it has the shape function. This has all the shape function, and u e has the nodal coordinates, that the not coordinates but local nodal displacements. So, this n matrix has all the shape functions, okay, in the element, and u e has all the nodal displacements, all the nodal displacements of the element. Yeah. Okay. So basically we also found out how to actually get these shape functions. Okay. So that if you have the nodal displacements, so these values, you have these values at the nodes, but if you want to find out the displacement here, then how to find out? So you exactly know what is the value of here, so this is this equal to this, at here maybe equal to this one, but what is the value in between somewhere we can find out using this interpolation function multiplied by this, you know, and you put the value of x or nodal coordinates. You put the value of x means the position where you want the value of u in these shape functions, and then you multiply and then you can get exact value of displacement at the point where you want. Similarly, given the displacement, you can also find out what is the strain, right. So, displacement you can find out at any point. So, displacement also you can find out any point. So, that really means du over dx also you can find out. So, due over dxe, right. This also you can find out, and this will be equal to nothing but your this becomes dne1 dxe dne2 over dxe, so on till dnen over dxe, and then you have multiplied by same thing here ue1 ue2 so on uen, right. So you have like this. So instead of saying like earlier we called it n vector, now the same thing you may call is equal to b, the B matrix multiplied by UE matrix, right. So where this B matrix has derivative of derivatives of shape functions. Yeah. So all these things we will study in detail in chapter 5, but here since chapter 4 has mention of B, and hence we have done here also mention of N. So just to prepare you for chapter number 5 basically. Yeah. So rest of the things we will study later on. The idea is if you look at this one, yeah, and we know that u is given like this, yeah, and the a shape, and also we know that for one element we have just if you see just one element, okay. So the one, this is one element, this will have du over dx ea at x equal to le, xe equal to le, yeah, is the value here, and this will be ea du over dx and xe equal to 0 value, and the weak form for just this element, for this element only, can be written as, so if you, even if some element is in the middle somewhere, say this is we are talking about these elements, this is what this element is, and if you cut it here, yeah, if you cut it here or here, then there will be a axial force here, right, axial force here, that will axial force and internal force. So that's what we are showing, this force here, that force will be equal to nothing but dEA du over dx, x equal to le, that this is what the force will be, this is what the force will be, yeah. So although it's not given, this is not a actually the natural boundary condition, so we assume this we have to find out, yeah. So this is not given basically, yeah, it is not given. And your x is the value of this, what will be the value here. So the value here will be u E0. So this may also not be given, either given or not given, yeah, okay, because this is from the middle. In the middle typically it's not boundary condition are given at the ends, but we are talking about one of the elements of many elements of the structure we have to analyze. In that case, what is the value here? So that's we also don't know. Basically, what we can treat both force and displacement as unknown. Okay, so general purpose we can write the big formulation, and this will be something like this: 0 to LE. Yeah, notice we have LE here, right? So okay, and then what we have? We have W E over dxe. Okay, so we are doing all calculation locally, yeah. Then EA, then du E over dxe, okay, will be equal to, and apart from this there will be in terms this as well, okay. So we can write the other side as well. So equal to, we will have 0 to LE, then B as a function of xe, W E xe dx, then plus we will have the this thing will appear here. So you will have D, sorry, you will have EA D U du E du E over x dxe, right, and multiplied by this will be x e equal to LE, should be multiplied by W at LE minus EA due over dxe at x equal to 0 multiplied by W E here also WE at 0, right. So this also we looked at in the last lecture video. So this will be the whole weak formulation when neither u is given at this at the ends of this element, yeah, nor the forces are given. This will be the general purpose like this one. And if we put now these values, so du E dxe value, similarly here also we can also write d w e over dxe equal to B matrix multiplied by WE matrix, where WE is equal to nothing but WE1, WE2 to WEN transpose. Okay. So okay. So basically we have this derivative ready here also, so we can put those values there. So these values and this we can put in the equation here, okay, and let's say this is called left hand side. So we can, so left hand side, if you see left hand side is equal to what do we get? 0 to LE, and we have n, right? We have n matrix. We have n matrix multiplied by UE matrix. Okay, not UE. We will have WE. First we, okay. So we have this equal to not n but B, sorry, this is B matrix, right. So B multiply WE, Okay, so we have dwe over dxe. So we, okay, so here instead of n we have b, sorry, this we have b. Okay, so the b matrix there. Okay, then ue, this is for due over dx term is this one, then e, then we have b times b times we dxe. Yeah, so which is equal to, yeah, which will be equal to we transpose 0 to le, then will be b transpose b ea d xe. Yeah, and then we have here ue. Okay, so we can rearrange this one. So this b times, since b times we equal to we transpose b transpose, right. So this b transpose will be, so this equal to this times this. Yeah, so you can because b times w is a scalar number, so we can take transpose of this will be equal to b times we only, because it's a scalar number, right. And hence you will have, if you have transpose of that, will be equal to transpose of this multiply transpose of b. So that's what we have, and we have inside this one. So and rest we take b from here, and then ea here, and then ue goes outside. Okay, and which is equal to, this will be we transpose, and this will be ke, is a element stiffness matrix, and this you have ue. Okay, so this is called element stiffness matrix. Yeah. Okay, so this k basically has the element stiffness matrix, that is in the last video lecture we had k11, k12, k3, all those things composed like this one. Okay, so you can see here this will be transpose b ea, but b transpose is what? You can have the ke, that means we can write ke is equal to 0, k equal to 0 to le, and b transpose b, then ea dxe. Yeah, where b that means that this ke has kij as the members which is given by 0 to le, and then you have what? B is nothing but the derivatives of b, a derivative of n, the shape function, and hence you will get dni over dx ei ea dnj over dxe. Okay, so there is no items here. Okay, so and dx. Okay, so this also we got last time, but we have used different perspective. So we know from here this derivative terms come, so why we can say kij. The other side of the right hand side also we can work out, and right hand side we have this value, then we have this also, we have this also. So we can WE LE, so this is the last one, yeah, so this will be the last WELE will be basically the WN EN we are talking about, and this is the W1 WE1, this one is the first one, right. So and plus this one. So here also if you see this, we write as right hand side is equal to first is 0 to L and then B. Let us write W first. W we know W is nothing but N, right, N matrix multiplied by W E, right, and then we have B e to the power, this is L, sorry, this is L E. Okay, so B as a function of x E, okay, and dx E, okay, plus we have some value, let's we call it f, okay, f n, we call it f n because it is at f equal to the nodal, so we say f n multiplied by w e. So f, let's call f e n multiplied this is w e at the last node, yeah. So this is just our notation, okay. So what we are doing, we are doing this one. So W E at L E is nothing but the last point, that means what is the W at the last, W E N it will be, right. So this is the W at the last node, and this whole thing we are saying this value we are calling it F n, yeah. So we call it F E n, okay, and this we are calling F E 1, yeah. So that's what that is, okay. Okay, and this is nothing but W E n, and similarly this one is nothing but W E 1, yes, the first one, okay. So now that's what we are writing there. So same thing we will write here also, minus F E 1 W E 1, yeah, okay. So now we can look at this also. Now we have this here, right. Now remember in this case we have taken this out for the obvious reason, you know that finally we get rid of W, you know. So this is that's why we have to bring it here, yeah. So for that we have to transpose this one, so that we can write the same thing as W E transpose multiplied by N transpose, so that W is outside. So we can write the same thing, W is equal to W E transpose, then 0 to L E, yeah, and then you have N transpose, yeah, and then you have B x E d x E and plus F E N, yeah, and then WE minus FE1 WE, sorry, WE1. You can write like that. Yeah. Okay. Here the everything now we can write also like uh, this WE has all the terms, right? WE will have WE1, WE2, so on, WEN. Yeah, so basically the whole thing we can write something like this is equal to WE transpose, yeah, okay, and then we will have here something like this. Let's call it FEB1, and then we will also have FE1 as well, right? Then we will have FEB2 and so on, and then you will have FEBN plus FEN. Right? We can write like that, where FEBI is equal to 0 to LE, and then you have N, right, NEIXE multiplied by BXE DXE, and you know the definition of this. This we have here already, right? So this is equal to FEN is equal to this here, this whole thing. Yeah. Okay, so this is the extra, basically something we are looking from the element perspective only. Okay, so we are disconnecting this element from the outer structure, looking at that, so that this is complete. We have to also get the forces within this forces by which they are connected, right? So that's why we have to add this one. This is another matter, that if there is no external forces, you will see that all these will be, say, for this is a value like this one. For this also, if you take the next element, this will be like this, and there will be force, same force here. So hence when you write in the force vector, both will cancel out. So this and this will cancel out. So that's another matter, but we are making right now, making it complete. Okay. Okay. Now this this is what this is, and the values FE1 is we know it is what is du over dx, and this is xe equal to 0, and similarly this FEN is equal to EA du over dx, and then this is xe equal to LE. Okay. So anyway, looking at here, this is common here, and on the left hand side, if you see, we have this, and sorry, in the right hand side we have this, and on the left hand side we have this. Both of them has this common, and since W is arbitrary, hence WE1, WE2, WE3, all these are also arbitrary. Okay, and because of that, what we have is simply this equal to this. So you can also write this is equal to WE transpose, yeah, and you have F E. Here you have F vector F E. Okay, so left hand side equal to right hand side, and that means W E transpose K U E is equal to W E transpose F E. Yeah, since W E X is arbitrary, hence W E1, W E2 and so on, W E to n number of nodes in that elements are also arbitrary. Hence K U, so K vector K E, we wrote K E, U E is equal to F E. So this is how we derive basically. This is now we know what you mean by the force vector. Now you know what is you mean by the stiffness matrix, and this is the displacement vector. Yeah. So we have stiffness matrix, we have this displacement vector, and we have this force vector. Okay. So this is the basic derivation for the finite element analysis, and based on this basic derivation we can find out what is the value of K for different kind of elements like 2 noded elements or 3 noded elements, 4 noded elements and so on.